Okay, I want to take a little closer look at one of the problems we worked on in class, and the setup was something like this. We had mass 2 sitting on a frictionless table, with mass 1 sitting on top of it. Mass 1 was attached via a rope over a pulley to mass 3. Gravity acting on mass 3 was going to cause mass 3 to move downward and mass 1 to move to the right. There's also friction between mass 1 and mass 2, so as mass 1 slides to the right, the friction force on mass 2 is going to drag it along with it. What isn't clear from the beginning of the problem is whether or not there's enough friction that mass 2 stays moving along with mass 1 at the same rate, something like this, or if there is a more slippery contact between mass 1 and mass 2, and as mass 1 accelerates, it slides over mass 2, pulling it along at a slower rate. So we don't know what the acceleration of mass 2 is. Is it accelerating with mass 1 or not at the beginning of the problem? So to proceed, we want to start by drawing free body diagrams for each of the three masses. Taking a look at mass 1, the green mass, where the rope is attached to it, there's a tension pulling it to the right. There's also a normal force from mass 2 pushing up on mass 1. There's a friction force between mass 1 and mass 2 that is pushing to the left, opposing the motion from the tension. And there's the weight of mass 1. On mass 2, the purple mass, we have the friction force between mass 1 and mass 2 that's pulling it to the right, causing it to move. We have the normal force from mass 2 acting on mass 1. From mass 1 acting on mass 2. We have the weight of mass 2. And we have the normal force from the table pushing up on the bottom of the mass. And finally, for mass 3, we have the tension pulling up on the mass and gravity pulling down on the mass. Once we have the free body diagrams, the next step is to get the x and y components of each of these forces. So we make a table that has an x and a y column, and each of the four forces that act on mass 1 are listed in a separate column. So looking at the tension, it acts in the x direction and has no y component. The normal force is pushing up in the y direction and has 0 x component. The friction force is pointing in the negative x direction. It's opposing the tension and has no y component. And the weight acts straight down in the negative y direction. We need to make similar tables for mass 2 and for mass 3 as well. The one thing to pay attention to is to notice that for this problem, we said that the positive x direction was going to be the motion that each of the masses were moving. That means that for mass 3, the weight is pointing in the positive direction because it is moving in the downward direction, the same direction as gravity. From these tables, we can now write down Newton's second law that says that the sum of the forces in each direction for each of the masses is equal to the mass times the acceleration in that direction. So looking at mass 1, we can add the forces in the y direction, just summing up that y column, n21 minus m1g, and that's going to equal 0 because mass 1 isn't moving in the y direction, it's only moving in the x direction. We can also add the forces in the x direction. T minus the friction force, mu times the normal force, is equal to m1 times a1. We can do the same thing for the x and y components of mass 2, and we'll only have one equation for mass 3 because it only has forces in the y direction. You'll notice that when I talk about the coefficient of friction here, I've just left it as mu for now because we don't know whether static friction or kinetic friction is appropriate. But we need to take a look at that now. And I want to think about what would happen if it were static friction. Well, if it were static friction, we'd have the situation where it moves like this. M2 moves right along with M1. and there would be no slipping between those surfaces. So how much static friction would I have? Well, the most I would have would be equal to mu s times the normal force on object 1 from object 2. So the coefficient of static friction times the normal force is the maximum value, and the amount of static friction I have would be less than or equal to that. Thinking about the y forces acting on M1, mass 1, back from our previous slide we had this equation, the normal force minus the weight was equal to 0. This tells us that that normal force we're looking for is just equal to M1 times g. And from here we can calculate the maximum static friction force. It would be mu s times M1 times g. Plugging numbers in, we'd get that the static friction has a maximum value of 20.58 newtons. So now we can look at what the acceleration of the system would be if we had static friction, and how much friction force would be needed to pull mass 2 along. So here are the equations from Newton's second law that we had, and you'll notice that in the x direction for mass 1, I have T minus mu times the normal force equals m1a1, and in the x direction for mass 2, I have mu times n21 equals m2a2. So I can combine these equations, basically take the fact that mu n21 equals m2a2, and plug that into the equation that I had for mass 1, and get a new equation that T minus m2a equals m1a. Looking at mass 3 and the equation that I've got there, I can rearrange that to come up with an equation for the tension. Now I've got two equations that include the tension and the acceleration. You'll notice that I've dropped the subscripts 1, 2, and 3 for the acceleration, and that's because all three masses are accelerating at the same rate. So there's only one acceleration in the problem, and I can say A1 is equal to A2 is equal to A3 and just call that A. So with this expression for T, m3g minus m3a, I can plug that into the equation that I just derived by combining the x equations for m1 and m2. Collecting my terms and rearranging this, I see that the acceleration is actually equal to something that makes sense. m3 times g, or the weight of m3, which is what gravity is pulling on, which is what's causing the system to accelerate, divided by m1 plus m2 plus m3, which is the entire mass of the system. This gives me, when I plug in numbers, a numerical value of 4.63 meters per second squared. Well, now I can say if mass 2 is accelerating with an acceleration of 4.63 meters per second squared, the friction force would then have to be equal to m2 times the acceleration, and m2 was 5 kilograms. So 5 kilograms times 4.63 meters per second squared means that I would have needed a force of 23.1 newtons, which is larger than the maximum frictional force I could apply of 20.58 newtons. Therefore, mass 1 and mass 2 don't move together, and mass 1 slides across mass 2. Fortunately, we don't need to start over. All of the equations we derived from our free body diagram still work. The only difference is, instead of talking about a coefficient of friction mu or mu s, we're going to need to use mu k, the coefficient of kinetic friction. I've rearranged things a little bit here, looking at the equations for m1 and m3. And the reason I've done that is because m1 and m3 are still going to have the same acceleration, but m2 is going to have a smaller acceleration. So looking at the equation in the y direction for m1, we see that the normal force is equal to m1g, just as it was before. Looking at the equations in the x direction for mass 2 or for mass 1 and the equation for mass 3, we find that the tension and acceleration are related, and we can combine these to form one equation that gives us the acceleration. Working through the math there, you see that it's 5.16 meters per second squared. And it's key to recognize here that we're using the coefficient of kinetic friction of 0.5 rather than static friction of 0.6 in this case. Looking at mass 2, we see that the mass 2 times the acceleration a2 is still going to be equal to the frictional force, but the frictional force is now going to be the kinetic friction force. So a2, when we work through the equation here, we get is 3.43 meters per second squared, less than the acceleration of m1, which is what we would have expected. Now that we've solved the acceleration, it's relatively straightforward to plug that value for acceleration back into one of our previous equations and calculate the tension. I've used the equation here that we had for mass 3 and find that the tension is equal to 35.2 newtons.